Hi everyone, my name is Kangle. Today I'm going to talk about our work FlashTex, Fast Reliable Mesh Texturing with LightControlNet. Part of this work was done when I was interning at Roblox. Our project aims to solve the problem of text-based texturing. Given a text prompt and a mesh as input, we want to generate a texture for it based on the text prompt, as shown in the example. There are a few existing works on this problem, while these generated textures look reasonable at first glance. There's a limitation that most of these generated textures have lighting effects baked into the generated color. This makes it unrealistic when put under different lighting conditions. Therefore, our goal is to propose a method for fast reliable mesh texturing and solve this problem by generating the relightable textures, which can be relit properly in different lighting environments. As a prior effort towards relightable textures, Fantasia 3D tried to use physically based rendering materials to represent texture instead of only color and apply a score distillation sampling loss. However, due to the inherent ambiguity that the same full-color rendering could correspond to different disentanglements of materials and lighting, Fantasia 3D's result still has a lot of baking lighting in their diffuse component. Here's a more in-depth analysis about why this would happen. In score distillation sampling, also known as SDS loss, we differentiably render an image from some learnable 3D representation. In our case, it is a fixed mesh with learnable texture. We then noise this image and push it through some diffusion unit, like Stable Diffusion. And we treat the output denoising vector as the gradients to update my rendered image to make it more realistic. However, the image is actually rendered with some specific lighting. The SDS loss is only designed to make the image more realistic, but maybe not in the right way, which is consistent with the lighting, because the diffusion model is not aware of the lighting. We propose to train a new control net to make the diffusion model dependent on the lighting. Thus, we need to define some type of conditioning image that encodes some lighting information. Here's our basic idea. We propose to use a shaded image under some specific lighting with default material. As you can see, the highlights and shadows in this control image indicate useful cues about the lighting environment around this object. And we train a new control net that could generate an image following these cues. In order to cover a wider range of different materials, we use a set of 3 different material bases and stack the 3 grayscale images into a single control image. And we train a control net, which we name it as LightControlNet, that generates an image following the lighting and the shape in the control image. This is an inference 2D generation with our LightControlNet. You can see the output images follow the lighting in the control image while flickering with appearance, which is expected as every frame is independently generated. To train our LightControlNet, we use 3D objects from the observer's dataset. Specifically, for each object, we construct a triplet as a training sample, where we render the object with its original texture and materials as the ground truth. We also render it with the conditioning materials as the control image. And finally, we use its name and tag as the text prompt. Importantly, we randomly sample the camera poses and the lighting during the rendering to make a diverse dataset. With our LightControlNet trained, we can replace the stable diffusion in SDS loss with our new LightControlNet. Specifically, we use a hash grid to represent our texture as PBR materials. And we randomly sample camera viewpoints and lighting to render images. The LightControlNet SDS also requires us to render the corresponding control image using the conditioning materials with the same potent lighting. This might give reasonable results, but the full SDS optimization usually takes an hour, which is too slow. We propose to speed up the process by initializing the texture with 2D generation. Specifically, given an input mesh, we first render the 4 canonical views with the canonical lighting, and run our LightControlNet once to get a reference image. With the fixed reference image, we use reconstruction loss to initialize our texture hash grid. But how do we get multi-view consistent images with 2D diffusion networks in the first place? If we generate each view independently, we will most likely get inconsistent outputs with different appearances even with the same seed. This is because we only have attention within single view. However, if we combine these 4 views into a single image and feed it to our LightControlNet, we will get much more consistent output, because now the self-retention could happen among pixels across different views. We empirically find that this multi-view visual prompting works reasonably well even without any fine-tuning on multi-view data. As we mentioned before, we back-project the 2D reference image onto the mesh to get an initialization. This could have some missing regions and artifacts when you try to stitch different views together, and also potential baked-in lighting. These issues could be solved by a subsequent LightControlNet SDS optimization, which is as quick as 3 minutes. In each SDS iteration with stable diffusion, the gradients are calculated in the latent space and thus need to be back-propagated through the VAE encoder. We analyze the running time and find that it almost takes half of the backpropagation time without doing anything important. To further speed up the process, we distill the encoder into a much smaller one, which runs 5 times faster without affecting the quality. With these 2 design choices, we cut our running time from 1 hour to only 4 minutes while keeping the high quality outputs. We compare our results with Fantasia 3D. As you can see, our results have much less baked-in lighting and are more realistic under different lighting conditions. We further show our method can generate diverse outputs with the same geometry and different text prompts. And our results can be put into various lighting environments and be relit properly. Part of this work has been incorporated into Roblox Studio as a feature of AI texturing. Please check out more examples in our code on the website. Thanks for listening.